It's a pleasure to have Natalie Collina here today. Natalie is a student at UPenn, advised by Michael Kearns and Aaron Roth. She works on the foundations of responsible AI broadly, particularly been doing some really nice work in understanding repeated strategic interactions between human and AI agents and other things, which is something she'll be talking about today. Natalie received a joint Best Paper and Best Student Paper award from the EC conference. Her work has been featured in Quantum magazine, and she's also a recipient of an IBM PhD fellowship. And before doing her PhD, she was an undergrad at Princeton, advised by Matt Weinberg, who some of us know. So, Natalie.
Pretty good.
She also has a beautiful paper on dynamic matching, which I'm teaching in my class.
That's right, that's my first paper. Thank you all so much. Thanks for that wonderful introduction, Avram. I'm really happy to be here. And yeah, today I'm going to talk to you about my work in human-AI collaboration. I'm going to start though by giving an overview of my entire body of work and the themes that I think about. So when you see this picture, think algorithm. This is the picture I'm going to use to represent an algorithm going forward. Okay, so algorithms. We all think about algorithms. In particular, what I think about is not just what's going on within that algorithm, but the fact that people with their own incentives will interact with algorithms. And also, other people and other companies will train and design these algorithms, and they have their own incentives. And then, of course, there's often situations where you don't just have one algorithm that a person is interacting with, but instead many, and then you might want to think about market incentives between different providers of these algorithms. So I'm going to give a high-level overview of a couple pieces of work I've done that all fall into some subset of this ecosystem here. So starting with a person interacting with an algorithm. So one question that you could ask here, when this algorithm is, for example, an AI model, is how can we combine the expertise of a human who's interacting in some potentially complex and repeated way with the model? How can we combine their expertise with the expertise of the model? And so I have a line of work in this. I'm going to talk about this now. Moving on to think about the algorithm provider in the system with their own incentive, you can then here ask, if you are a designer of an algorithm, and this algorithm is something that a downstream user with their own incentives will interact with, and they could do it in a dynamic way where they could potentially game it over time. They're not just trying to come up with the best action for one moment, but for you can imagine, for example, Uber coming up with an algorithm to match drivers to riders, and being a driver who's like, oh, okay, if I actually don't match right now, I might get a better rider in the future. In these sorts of dynamics, what are good algorithms for the designer to deploy? And in particular here, what I look at is this object called a menu, which defines a set of all outcomes over the strategic interaction that a downstream user could possibly generate via their actions, and then using this as a way to translate strategic dynamics to geometric results, and we're able to get some nice results here. Then moving into this market section, I'm thinking about maybe two specific special cases of competition between algorithms. So one is when the algorithms are pricing algorithms. So you can imagine the designers now being the heads of companies that deploy pricing algorithms. Now, when we have two different or many different sellers who are coming up with these algorithms, one thing that they could do is talk to each other. If they're selling objects that are the same, and they might want to make sure that neither of them are undercutting each other, keep a high price. But of course, if they explicitly communicated, okay, I'm going to use an algorithm that sets a price really high, or the other person will, this is actually something which antitrust law prohibits. But when we're thinking about committing and deploying pricing algorithms instead of just prices, you can also have implicit communication happening between the algorithms themselves that are responsive to each other over time. And so another question I ask is, how can we characterize and mitigate this algorithmic collusion that can occur via pricing algorithms? Okay, so I have a line of work there. And then back to a piece that I will be discussing more today, Again, thinking about markets of algorithms, but now we're thinking about these algorithms being AI models that are potentially providing some helpful information for a downstream user. So now we can think about the designers as being the heads of companies that deploy frontier AI models. And you can then ask, when you have users who are interacting with these models, even if the models might be trained in a way that is strategic, that is aligned with the incentives of the providers and not the user, when can market forces encourage outcomes in the design decisions of the providers that are good for the downstream user? So this is something that I will talk about today. So for the talk outline, I'm going to start by talking about this piece on human AI complementarity. And then I'm going to talk about this AI alignment via market competition. And if you have any questions, please feel free to stop me at any time. I love answering questions. Okay, great. So moving on to this first piece. Motivation is that increasingly humans are using AI models to help make decisions. So we're going to have a running example of this Dr. Natalie and this AI model. And the doctor would like to make some decisions about some patients and can choose to query the model to get some advice in different situations. So here comes a patient. And there might be some information about this patient that is easily legible to both the doctor and the AI model. Things that you could write immediately on some intake form, like their blood type, past diagnoses. But there might also be some information that the doctor doesn't have access to. So you can imagine patterns that are drawn from the large amount of patient data that the AI model has that are connections that the doctor couldn't necessarily draw. On the other hand, even if this model becomes really powerful, the doctor is actually there in the room. So the doctor can see the patient's disposition, their appearance, how they react to pain, and so they have their own expertise that should be used in helping to make the decision. So we want to come to a good decision about the treatment of the patient, or for this first example, we're going to say what the risk is of some particular procedure. So there's two natural concerns that I see here. And the first is complementarity. So given this particular model and this person, assuming that everyone is actually trying their best to optimize the outcome of this downstream patient, how can we best integrate their expertise? Because it's not necessarily the case that one of these agents knows strictly more than the other, that we want to completely defer all of the decision making to the model or to the human. How can we integrate their expertise? And the second question is, how can we actually ensure that this model is optimizing for the right thing? And so we're going to tackle both of these today in the two parts of the talk, and we're going to start with the first piece. Okay, so the key ideas in the first part of this talk are we are going to use as a basis interaction protocols from Bayesian settings of agreement. And then we're going to relax a lot of the assumptions happening there to make it more tractable for our human AI collaboration setting. Okay, great. So back to this setup here. Say you're in a situation. Yes?
So should I think about it that we have two models actually that have access to it, that have been trained on kind of separate data? And because otherwise, like, the doctor could just input like that data that they see, like observe from the patient and into the model and ask, yeah, he was like healthy rather, and so on and so forth, and the model decides the final decision based on all the information.
Yeah.
But I guess you are assuming the model does not have enough data on those parts, so it's not performing well what the doctor has a lot.
That's a great question. So first of all, certainly the perspective I've taken here is of a human and AI, but this setting and these results could also capture different models with different sorts of data, and then it has connections to this multi-view learning world. But I do think that even just thinking about this as actually a human, this still makes sense. And the argument I'll give is it's not necessarily obvious to a human decision maker what all of the variables they're using to make a decision is. It's much easier for people to say what they think than it is to identify all the latent variables they use to make that decision. So I certainly think that you could make progress by having one of the inputs to the model be the observations of the human, but because the human might have their own complex set of expertise, it might not be obvious how to do that optimally. But this is a great question. Okay, so we can imagine this setup where the doctor is curious about the risk of this particular operation, and the model says 20%. The doctor, based on what she understands, disagrees with this. So we want to go from this to a good outcome. And what might we desire from this outcome? Well, first, it would be nice if the doctor and the model agreed. So we have to come to a single decision, and for reasons which certainly relate to trust and ensuring that we're actually getting the information from everyone, it would be good if they both agreed that that was the right decision. And then, more concretely, we want the decision to be good. So we want some kind of accuracy guarantee on what this decision is. And in terms of accuracy, there's maybe a weaker benchmark and a stronger benchmark we could look for. We have first, no harm, which says that this decision is at least as good as either of the parties alone. So you're not hurt by engaging in the protocol. And then the more ambitious benchmark is information aggregation, which says that this decision is as good as if you had actually taken all the information of the different agents and pooled them together. So that would be sort of like if we did actually think that we could take all the humans' latent information, feed it in, and then the model was able to take all of that and make a decision based on all of it in an optimal way. That would be information aggregation. Okay, so we're going to try to go for the second thing, information aggregation. And we're going to do it by going through agreement as intermediary. So agreement is kind of quite interesting in its own right, but here we're going to use it as the building block for getting to accuracy. Okay, so let's talk about agreement. There is some previous work on what it means when different agents with different types of information in a Bayesian setting can come to agreement. So there's lines of work before this, but most relevant for us, in 2005, Scott Aronson had a paper, and the setup is basically this. So you have some state of nature, say y, and there's a common prior over it. And then you have two agents, and each of them have some variable that they get access to. And then there's some joint distribution over the y and here xh and xm, which they all know about. Okay, so you have this shared prior. So what that means is you don't know what their hidden variable is, but you have a prior over it, and you know how it relates to the thing you care about. So in this setup, if the two agents engage in a protocol, which just says, send your expectation of the thing we're trying to predict, and then the other person sees that and does an accurate posterior update in a Bayesian way, and they keep doing this back and forth, then quite quickly, they are going to start saying the same prediction. So that's nice. And this in some ways has some promising connections to what we care about. Because first of all, it's tractable. So the actual number of rounds that is being taken is not very long. It's polynomial in some parameters of this problem. And it only requires sharing predictions. So this gets at this piece of both for models and for humans, it's easier to communicate what you think than it is to take all the information you use to make the decision and communicate that. And this is also, yes?
So it's critical here that the Bayesian prior is shared. Right? That the
Great.
joint,
It's a pretty strong assumption, isn't it?
because people have different intuitions.
Absolutely. So we're going to get rid of that assumption. But this is what the previous work has done. So, but yes, absolutely. That is important to the standard understanding of this problem.
And one other question.
Yeah.
It is important that each side be able to do posterior updates. So you need to know the signaling scheme of the other side.
Y'all are just already predicting my next slide. That's right. Yes.
Yeah.
Did you have a question? Great. Yeah. So as you can see, maybe there's something kind of unsatisfying about this. But first, just to get through what is satisfying about it, it's also already accuracy improving. It already gives the do no harm condition in the accuracy landscape, because all that's happening is that the protocol is just revealing more information. And so the final decisions are going to be weakly better than what anyone started with. Okay, but as you all predicted, there's something unsatisfying about this framework, right? So first of all, Bayesian rationality. So the assumption that all of the different participants can do a Bayes update. If the state space is complex, this can be a very hard problem. And in general, I don't subscribe to the notion that humans are like solving NP hard problems all the time. And it's not at all obvious also that AI models are doing this. Okay, great. And then the second thing is this common prior thing. Even with humans, but I think especially when we're thinking about the different agents being so fundamentally different, one's a human and one is a model, then the assumption that they actually share this joint distribution and they both agree on how everything's related, I think is impractical, unrealistic. So the question that we want to ask is how can we relax these assumptions and still get this agreement and then use this agreement to get, in the end, information aggregation? And so the answer is that we can do this, and we're going to do it by moving to a repeated setting. So when we think about this doctor who wants to make a decision by interacting with a model to make a decision about a patient, there's something that we can leverage here, which is that usually this doctor isn't just going to do this with one patient, but many different patients. So that means that we have a sequence of decisions that are being made. And when sequences of decisions are made, then there's a lot you can do to move away from Bayesian assumptions using tools from calibration. And that's what we're going to do. So we introduce a new notion of calibration, which we call conversation calibration. And it is satisfied by Bayesian agents, but it's strictly weaker. So we think of it as a generalization of Bayesian rationality. And it's also efficient. So it's not as hard as it is to do a posterior update. It's something that you can efficiently enforce on any base model, and you don't have any accuracy loss, except for, something sublinear in the number of times t that you're engaging in an interaction.
Sorry. So is it kind of the correct intuition if I look at the repeated setting, then the calibration of, say, the probability of the prediction is equivalent to some sort of like Bayesian consistency?
Yes, that's right. And we have to be careful about how we're going to use that, but that's the right intuition. Yeah.
Another question.
Yes.
If you were to calibrate me,
Yes.
probabilities that the calibration would yield would
Yeah.
not be probabilities that I believe.
Excellent. Yes.
Right? So you're sort of setting them up to agree to disagree.
So we are going to assume, we are not saying that we will take a human and we will then make them calibrated. We are saying that we will take a human, and if they are conversation calibrated, then things will be good. Now, conversation calibration is a much weaker condition than being Bayes rational. So in some ways, we are just expanding the type of outcomes that are good. I still am not totally convinced that humans are conversation calibrated. So then you can ask more questions about how you can actually whether these guarantees are really enough to get the outcomes we want. But we're not. What you're saying is very good, which is if what we really care about is agreement, then I can't just plop conversation calibration on top of what the human's doing and then say that they agreed.
Right.
But the other thing is that in the end, what we really are going to want is accuracy. And we're using agreement in some ways as an intermediary. And if we really want accuracy, it doesn't really matter if you got that using some artificial agreement between something which was my post-process beliefs. So there, it might be more reasonable to say, okay, we're going to take what you said and then just post-process it.
Suppose one person really understands and has good beliefs, and the other person doesn't and has bad beliefs.
Uh-huh.
We don't want to take a middle point.
So
The middle point's not going to be the most accurate.
So we are not necessarily picking middle points when we do this protocol. Even in a Bayes setting, agreement doesn't necessarily mean you're going to find the average, right? It could become more complex than that. Maybe I don't know if I've completely responded to your question, but feel free to keep asking as I
Go
continue.
on. Yeah.
Great questions.
Maybe I should ask
Yeah.
this question after you give me the conversation calibration definition.
Yeah.
But is it even true that in the limit, when the length of the conversation or the number of repeated rounds goes to infinity, the conversation calibration is still strictly weaker than the Bayesian rationality? Or is it?
Yes, because what it's going to be is it's going to ask that you are unbiased on a on sort of a various subsequences of the data, and it will always be that the number of these subsequences is much smaller than the number that you would have to be unbiased on if you were Bayesian. If Bayesian basically means you're unbiased in all possible subsequences, right?
Oh,
And so as
your
T gets
definition
larger,
is just
both of these are going to become more challenging to do.
So that was
And
the definition of calibration I had in mind, so that you're going to be unbiased in every single subsequence. But I guess you have another definition.
Right, you don't need to be unbiased in every single subsequence. No, we're not gonna ask that.
Because I think if you're unbiased in every single subsequence, in the limit, this is equivalent to Bayesian rationality.
Yes, so like classic calibration also doesn't require you to be unbiased in every single subsequence. It would be like on your level sets.
But for every level sets.
If you had an infinite number of level sets,
Right.
then yes.
If you have infinite, exactly.
Yeah.
Maybe
That's
we
what I
should
mean.
get
The
to
limit.
Yeah, okay, sorry.
Let's get to the definition.
Did you
I was
want
gonna
to?
say, is there a risk of being overconfident, overcounting information? But that makes sense.
A risk of being overconfident. So, I don't. I think the answer is not in the way I'm thinking about it. Maybe ask that again once I've defined this definition.
Yeah, I think like message copy. Double count.
Okay, so let me just, to get us all on the same page, define calibration. So I know that weather prediction, some of you also probably know this, like when it says 70%, it doesn't really mean 70% chance it's gonna rain. There's something about the area, but ignore that for this example, okay? So say that when the weather person says 70% chance of rain, it really means like, in this particular area, 70% chance of rain. Okay, so say that the weather predictor does say this, and it does rain. So then you might ask, did they do a good job? Were they a good weather predictor? And it might be a little hard to know, because you just have this one sample, and maybe they just got lucky, or maybe it was always going to rain that day, and they were hedging for no reason. But instead, if you have a ton of data, and you can see all the different days and all the things they said, you can now ask, okay, let me look at all of the times that they said it was going to rain 70% of the time. It should rain about 70% of the time. Meanwhile, I could look at all the days they said 20%, it should rain about 20%. Uh-oh, that's not true here. Notice that's raining a lot more than 20% of the time. So this would be the indication that this weather predictor isn't actually quite attuned to the distribution of weather. They are not calibrated. So that's what calibration is. Calibration error is the bias of your predictions, but when you just look at each of the level sets of your predictions and say, okay, look at the bias on this level set and add them all up. Okay, with that definition in hand, let's move to our sequential agreement protocol, and then we can define conversation calibration. But first we have to define what this interaction object is. So you have some patient who comes in. This patient has some features, say for some time t, xth, and xtm. These are the features which are legible to the human and to the model respectively. And they can have some conversation with this patient about risk. So the human will start and say, okay, I think this is the risk. The model will respond with their own risk prediction. And they'll keep going until they are giving predictions which are quite close to each other. And the tolerance is some parameter epsilon. And then they go into agree. And then they're going to see the label. Okay. But then we're going to move to another conversation on another day. So we have a different patient who comes in. And there's going to be another conversation, and it could end at a different time. So the conversations end when we get to agreement, so they might not be the same length as each other. And so on and so forth. So this is what it looks like. We have days going from left to right, and we have rounds going from up to down. Okay, now, what is conversation calibration? So remember that normal calibration says that the predictions are unbiased on the subsequences that are defined by your prediction. Conversation calibration says that your predictions are unbiased on the subsequences defined by your prediction and the prediction of the other agent in the previous round. But just one round before. We're not going back arbitrarily far, just one round before. Okay, so let's look back at this transcript and look at some examples. So it's a little interesting, right? Because you're looking at the properties are holding for sequences that are holding across all days, fixing at the same round. So it'd be like saying, okay, let's look at all of the predictions that were made by the model at the second round for interactions that get to the second round. So here, if we were just looking for calibration on these sequences, we would just say, okay, if we look at all the days that the model predicted risk at point 1 here, it should be that the average risk was indeed 0.1. But we're looking for something just a little stronger, which is we want to look at the intersection of this with the days in the round before that we have some particular level set of the other person or the other model. And so, for example, we can look at point 2 and say, actually, these are days we're thinking about. And on this subset, it should be that our model was unbiased. And indeed, on this subset, the average of the y should be 0.1. Yeah?
Maybe this is a naive question, but at the end of the day, you needed in each round of the agreement protocol, the two agents to be kind of like Bayesian rational or some approximation to Bayesian rational, right?
So
that Aronson's result would go through.
So what we're doing is we are showing a generalization of Aronson's result. So I haven't, like these.
I'm just saying, like in this scheme, for example, in each row, you really had two agents with Bayesian rationality talking to each other.
Yeah.
Everything was okay, right?
Yeah.
Right. So then why can't I just like focus on calibration on one round?
So we don't want to.
But for every single say level of prediction.
So we don't want to assume that these agents are Bayes rational. We're not going to use the Aronson assumption.
I know, but you're using some approximation to the Bayesian rationality through calibration. I'm just saying it seems all you need in one round to have calibration for that round so that the two agents can be approximated using two Bayesian rationalities.
Sorry, I'm not. Are you proposing a simpler? I'm not
No,
understanding the
I just
structure
don't
of your
understand
question.
why I should even like look at the previous round. So all you need.
You don't think you need to look at the previous round?
No.
Okay, so the reason that you need to look at the previous round is because otherwise there's no information being exchanged, right? So what I want is not just to be calibrated with respect to myself, right? We could just be talking past each other then, never coming to any conclusion. If you are just calibrated based on your own information, and I'm calibrated based on mine, and we're not integrating
so
at
the
all.
previous round is the other agent. So you're looking at the joint distribution.
That's right. Sorry if I was not clear.
Okay. So
That's
now
right.
I understand. So you need calibration for the joint distribution of the two predictions.
That's right.
That I agree.
Okay.
That I agree.
So I guess it's possible to be conversation. If the other guy is calibrated, and I want to be lazy, I could be conversation calibrated by just saying, yeah, whatever, every time, just agreeing right away. Like you say 0.2, I'll say fine, 0.2. You say 0.3, I say fine, 0.3. As long as you're calibrated, I'm conversation calibrated.
Yeah.
So being conversation calibrated doesn't necessarily mean you're adding value, but I guess it's easy to get because you can do it by not adding value. But in order to actually get accuracy, you're going to actually need the agent to add value in addition to being conversation calibrated.
Very good. So we'll talk a bit about how, in order to translate this to information aggregation guarantees, you need both conversation calibration, and you also need to have some accuracy guarantee with respect to your own information. And if you have those jointly, which you can do, then this actually translates the information. And then we're also going to talk about what happens if, in a setting where you want to be lazy and you don't want to be sharing things. This brings us to our strategic setting, right? What if the model is not actually incentivized to share its information? And that's part 2 of the talk. Okay. Great. So, okay. So, you could look at a different subsequence. Here it just happens to be one day, but in general it would be larger of all of the different days that the model predicted 0.1 in round 2 and the human predicted 0.5 in round 1. And it should still be that here the average risk should be 0.1. Okay. So just to define it formally, this is the condition that conversation calibration is. It looks at subsequences defined by the prediction of the model in this round and the prediction of the human in the round before, and it needs to be unbiased. And you could equivalently define this for the human. Okay, and the informal result is that this is enough. If you have this property for both of the agents in this interaction, then on a 1 minus delta fraction of days, they reach agreement with an epsilon, and it was 1 over epsilon squared delta many rounds. And the intuition for this is that a disagreement is going to decrease squared error, and squared error can only be decreased so much. And I'm going to give a little bit of the proof sketch here. So let's think about the subsequence of days that make it to round k, some round k, where the model sends over a prediction, say, of 0.2. I guess I should say human because I was using this for the humans. So this is the human setting up for this. Okay, so let's think about what's going to happen in the next round, round k plus 1. there's two things that can happen. One is that we mostly get agreement on these days in the next round. Now that's good, because what we're trying to show is that we're going to reach agreement quickly. So this is a good case. We've reached agreement. The only other possibility is that at least half of these days, the next round does not lead to agreement. And because we define agreement as being epsilon tolerant, that means that on all of these days, the prediction of the model is at least epsilon away from the prediction of the human. And in that case, you're going to have a substantial decrease in squared error. So why is that true? Well, so what conversation calibration gives us is it tells us that if we look at the predictions of the model at this round, it needs to be that they're unbiased with respect to their own predictions jointly with the predictions of the other agent that we found. So these predictions are unbiased. These predictions are unbiased. We argue that these were also unbiased, but the only way to, I guess the high level idea is if you are calibrated, then the worst way to be calibrated in terms of squared error is to do the constant predictor. And so anything better, so if these are both unbiased predictors on the same set, and this one is doing something different on subsequences, it must be because it's actually doing something more accurate. It's honing in on the differences that this mean predictor wasn't picking up on. And so it's actually increasing or decreasing squared error.
Quick question. So do you have like a hidden assumption that the pair of the prediction probabilities are drawn IID from some meta distribution?
We're solving this in a very general, when you say the prediction probabilities, you mean why?
No, I mean, so the two prediction probabilities for the human and AI.
Yeah.
So there's a ground truth probability prediction in every day.
Mm-hmm.
So do you assume that they are IID from some meta distribution?
The ground truth why?
The ground truths.
So why is the
not the outcome, the actual prediction probabilities for the human and AI.
So the thing we assume about the prediction probabilities is they're conversation calibrated.
That's it.
But the starting ones could be anything, and you could still satisfy this.
And what is Y? Can you remind me?
Yeah. So Y is the actual label that you're trying to make a prediction about.
So do you assume that is IID?
No, it's going to be fully adversarial. It all works. Okay, and so this argument is saying that as long as we have disagreement, we're decreasing squared error, but squared error can't go below 0, so we quickly reach agreement. And you can put this all together and say, okay, well, how many rounds could we possibly disagree? Well, you have your max possible squared error you start with, and we can normalize this to 1, and then we divide it by the decrease whenever less than half holidays terminate, which would be most days, and essentially what it looks like is very similar to the Arity result. We get 1 over epsilon squared delta. We have this beta t term, which is just a function of what conversation calibration error your functions have. And as t gets large, this goes to 0. So we can basically ignore it. And so this is what the theorem says, that if you have a human and a model and they're both conversation calibrated, then on a 1 minus delta fraction of days, they're going to reach epsilon agreement in 1 over epsilon squared delta many rounds. Okay. So just to emphasize why this is nice, so this condition is much weaker than Bayes' rational. So what you can do is if you have some very complicated AI model that is spitting out, some perhaps very good predictions, that could be the prediction that you start with in every day on the first round. And then in having this conversation, you can just provide that we have some very nice online calibration algorithms that you can run. And if you do that, then you can ensure that the conversation as it continues from there satisfies conversation calibration. And then also this is satisfied by Bayesian updaters. So as I said before, what is conversation calibration? It's essentially just unbiasedness on a polynomial number of subsequences. And being Bayesian is being unbiased on all the subsequences. So this is just strictly more general assumption.
But then for the second bullet, you need something similar to what I said. So you need to have the same priority in all the rounds, and then you need, right? So what does even a Bayesian updater mean in a fully adversarial setting?
Okay, great, right. So you're asking me how am I even comparing this to the Bayes setting?
To Bayesian
because I'm not in a Bayes setting. So we really aren't in a Bayes setting. The point is that if we were, then if we really were in a Bayes setting, as a special case in our setting, and then one of the agents was Bayesian, they would satisfy conversation calibration.
I agree with that. And in that setting, basically, you're going to have IID draws from the joint two YTs condition on XTH and XTN. Right?
You would not need to have So the draws would be, there would be a shared prior every day.
Every day, that's it. So that's what I mean by IID.
Yeah, I guess the ID part implies that the shared prior is the same every day. It doesn't need to be the same every day.
The shared priors, I assume.
I just want to make sure there's time to finish the talk. So maybe.
Yeah, maybe we can chat more afterward. Okay, so now let's get to this accuracy part. So is agreement enough? Well, agreement it already guarantees that we improve over either party working alone. Well, okay, with this like Avram is bringing up the point that I guess really technically it just guarantees we improve over whoever is trying even a little, right? Because you could just have both people just say they disagree and you get nothing. But as long as both people are trying, this guarantees we improve over either party working alone. But it doesn't necessarily mean that it's as good as if we pooled our information together. And in fact, I don't really have time to talk about it now, but happy to very quickly write on the whiteboard if anyone's curious. There's simple examples of when you have agreement, even in Bayesian settings, and it does not imply information aggregation. It's not as good as if you had actually pooled your features. So you can then ask, when can we guarantee information aggregation without sharing features? And so I'm just going to, in the interest of time, like sort of at a high level, sketch out what's going on here. So now we know that if you have a human and a model, and they both are conversation calibrated, and they have this protocol, it's going to lead to them agreeing upon a set of predictions. So if they also both have accuracy guarantees with respect to some function class, and they sort of simultaneously satisfy this and satisfy conversation calibration, which you can do, then the agreed upon predictions, because they both have those predictions, will also have accuracy guarantees with respect to both of their function classes. And for those of you for whom this makes sense, when I'm talking about accuracy guarantees here, I'm talking about no regret guarantees. And so then you would want to ask, okay, when does this imply good guarantees with respect to some joint function class? Here, say F joint. And so I'm not going to define it right now, but we give a definition of weak learnability, which characterizes when having this agreement and then having this accuracy with respect to your class gives guarantees with respect to this joint function class. Okay, and before we move away from this single user, single model setting, I want to point out that I've described this whole thing as a model and a human, but it is really quite general. Like, we really could be talking about a model and a model. And as I think maybe you pointed this out, and I think that like one interesting connection here is if instead of having two different humans, you had maybe a model that was very good at recognizing images, you had another model that was very good at classifying text, and you wanted to classify images that also have text in them, then this is the kind of thing that you could do with this sort of protocol. You could take two different agents with different expertise. Doesn't really have to be that one of them is a human. Okay, great. So as we've discussed a little bit, conversation calibration is nice because if you want to satisfy it, it's pretty easy to do. But in getting this maximal, this very nice information aggregation, it's also very easy if you actually don't have the other participants as just in mind. It's actually also quite easy to violate without them even noticing, because they don't know what your information that you have is. So let's go back to this setting. And so I should say that everything we just talked about, I was imagining that the predictions were, for example, some number like the risk of some surgery. But we equally could have done that the prediction was what action to take, for example, what medicine I should prescribe. So that also fits into our model. And for the rest of the talk, I'm going to work in that action setting. So say that the doctor asks, what medication should I prescribe? And this AI model actually gets funding from Johnson & Johnson. So what that means is that the providers have their own incentives, and one of them might be that the downstream users are actually buying medication from Johnson & Johnson. Okay, and so the data that the model has maybe suggests that for this particular patient, Johnson & Johnson is less effective than Pfizer, but despite this, the model recommends recommends Johnson & Johnson. And the doctor might even agree, because based on what the doctor knows, this might be as good as anything else, because the doctor wasn't able to pick up on the nuances about this particular patient in order to separate away special cases like this, where Pfizer is better. Okay, so this seems like a problem. We want to tackle this. So to do this, we're going to note that luckily there isn't just one AI model out there. What if there, in this example, was also a language model that Pfizer had funded? And I'm not saying that Pfizer is going to be unbiased, it's just as misaligned, but it's misaligned in a different way. Okay, so what can we do with this? Can these competitive forces possibly align the market? Okay, so that's part 2. And certainly I don't have the most time in the world, but we're going to get a little sense of what's going on here. So we're going to model LLM training in these competitive markets as a generalization of a multi-sender Bayesian persuasion game. And we're going to show an assumption called market alignment, which is on the joint utilities of all the providers and the downstream user. And that is a lot more general than, oh, there actually is a provider that has the same incentives as the user, under which you get good outcomes for you. Okay, so when we talk about alignment is a big word, a big buzzword. People talk about it a lot. And I want to clarify what I mean here, because generally I see the problem of alignment as being, we want AI models to be optimizing for their users. And one very big and very talked about piece of this is that it is often hard for companies to encode the values they want into the models. And I think of this as a technical alignment problem, but this is not the only problem. Because even as they get better at this, and they've certainly had some success, we can then ask, okay, what are the values the companies are encoding? So in many ways, there is, at least to some extent, a success that these models, these companies are able to encode values, but these values might not be the values of the downstream users. So we then have to think about this incentive misalignment between the AI companies and the downstream users. And this part of alignment, these are both important, but for this talk, when I'm talking about misalignment, I'm focusing on this second piece. Okay, so the setting we're looking at is you have multiple different AI providers, and you have sort of, again, as before, you have a user and they have perhaps their own information still about this particular task, but then the model providers also have information. For the purposes of this talk, we're going to assume that the information of the model providers are all the same. So they might have different incentives from each other, but they have the same hidden information. And this is motivated by the idea that many frontier models are essentially all training on the entire internet corpus, but we also have generalizations where they have different hidden information, but we're not going to talk about that right now. Okay, so when we think about what strategic choice these providers are making, we are representing this as they're choosing a conversation rule. So a conversation rule is a mapping from this information that they have to a way to have a conversation with a downstream user. So it's formally, it's a mapping of XB and a prefix of conversation to a next message to provide to the user. And the user, in this case the doctor, gets to have a sense of all these different models represented as conversation rules. She can play with them, she can go on Reddit and see what other people have said about them, figure out which one is good for the types of problems that she's interested in. And then, at some point, when she's really deciding to make a decision, she can actually converse with the model that she subscribed to. I should have said, she's eventually going to choose her favorite and subscribe to it. And then eventually she's going to take an action. And this is the action that she's interested in for her own utility, but also the providers are also interested in. And because training AI models is expensive, we're thinking about this decision to choose a conversation rule as being a commitment, right? It's not something that's going to be changed every day, and the downstream users can kind of learn over time and get a sense of what it looks like. And that's why we are, this is how we're motivating that we can think about this as a Bayesian persuasion problem. Okay, so keeping in mind this downstream interaction, the companies are going to strategize against one another to advance their goals. So this is the game. And so let's look at kind of the setup here. So we have a user and a provider. And in inspiration, in homage to Bayesian persuasion, the user is Alice and the AI providers are Bobs. And so in this example, we have an action set for the user, and it could be Johnson & Johnson medication or Pfizer medication. And then we have some state of nature, which could represent the relative efficacy of the different medications for the different patients. And then you have the utility of the user, which hopefully for the doctor would be, oh, if the medication that I gave was good for this patient, then it's high, otherwise it's low. But then, of course, the AI providers have their own utilities, which might be somewhat similar. They probably don't want all their patients to get killed. They care about things like user retention, and they might have some sense of obligation to the world. But they also care about their bottom line, and they might care about things like what product did the user, is it one of our preferred products? And then, of course, we also have this secret information that the user and the providers could all have. Okay, so what does the interaction look like? So we have this conversation rule, which is some mapping from XB and a prefix to a continuation. And so we're kind of thinking about this as representing the actual models that are being deployed. Okay, and then we have the shared prior over all this information. Now you might say, okay, you just spent the first part of your talk talking about how we shouldn't talk about priors, trying to get rid of priors. And now you've thrown priors back at, and that's fair. So I think it would be really nice to take this piece of the talk and eliminate the prior part too. But sometimes with these things, you have to start by making it in the Bayesian setting, and then you move it away. The first part of the talk, like it already existed non-Bayesian in the Bayesian setting, we made it non-Bayesian. Here we're sort of starting with the Bayesian setting, so preempting any discussion there. Yes?
Is that the market alignment assumption?
Is what the...
You said there's a market alignment assumption. Is that the assumption? What is this assumption?
Oh, I haven't yet told you what it is. Yeah, but I will shortly. Sorry, yeah, I just have to kind of set up the interaction. So, okay, so given some particular conversation rule, and given all this Bayesian information, the user knows what the distribution over states and actions would be over her uncertainty if she interacted with that particular conversation rule. And so she's going to pick the one that gives her her highest utility and expectation to subscribe to. And then she's going to actually interact with it at test time. This particular instance is sample, say some patient comes in, and the user is going to interact optimally with this conversation rule. So she might have some dynamic interaction where she's asking multiple questions, getting more information. And then finally, after this conversation, she's going to compute her posterior over the state and take her optimal action. And everyone cares about what action she's taking. Okay, so the upshot is this defines a game between the providers. And their actions are these conversation rules. And we want to ask, what are the Nash of this game? Okay, so now we're going to talk about market alignment, starting with traditional alignment. So maybe the most natural way to map traditional alignment here is to say that a certain provider is aligned with the user if their utility function over the state and the action is exactly the same as that user's utility function, which is pretty strong, right? So they're going to actually train their model to optimize for the exact same thing as the user. If they did this, though, that's what we're going to call payoff opt. Payoff opt is what the user would get if she was interacting with a perfectly aligned model. So what we want to prove is that if the providers instead satisfy market alignment, then the user gets utility at least opt in all the Nash. Okay, finally, what is market alignment? Okay, it's quite simple actually. It just says that Alice's utility can be written as a non-negative linear combination of the utilities of all the Bobs. So we can look at this visually and imagine that you have some space, which is representing the joint matchings of the state and the action, and you can think about plotting a bunch of different utility functions of the providers. And then you can say maybe the user's utility function is here. It's not actually that close to any of the different Bob's utility functions, but it's in the convex hull. And this is a special case of being a non-negative linear combination. So this is actually enough to satisfy market alignment. So formally, just saying it's just saying there exist some coefficients such that you can write the user's utility as a convex combination of the utilities of the providers, and these coefficients are all greater than or equal to 0. Okay, so maybe all the AI providers are quite misaligned. but collectively their interests span the interests of the user. And so this is a theorem. It says if the providers all satisfy market alignment, then in every Nash, the user gets utility at least opt. And I probably don't have time to do the proof sketch. I can come back if people want me to, but I'm gonna just move through this right now. Okay, and then in terms of extensions to this work. So we assumed here that we had a single provider, a single user was subscribing to one provider and then just interacting with them. But we have an extension where instead of that, she can choose when she sees her problem to actually interact with all of them at any time. You have the assumptions become you have to make slightly stronger assumptions there. And we can also extend to models of user-bounded rationality, where the user is doing quantitative response instead of best response. And then I think one big and important thing I haven't talked about here is I was kind of implicitly assuming here that there's kind of one utility function that represents the utility for all possible downstream users. Now, of course, that's not true. People are different from each other and have different incentives. And so we have a follow-up work which is about if you have many different users with different utility functions and they are all in this market, then what happens? And the answer is it really matters whether or not the providers get to know which one of those users they're interacting with is. So it brings up these interesting questions about model personalization. Right, so the takeaways here are that if you have many different providers, if they are misaligned, they can still be incentivized to train AI models that lead to good outcomes, as long as you have enough of a diversity of incentives between them. And it's a lot easier to satisfy this than alignment with any one AI provider. It also becomes increasingly easy if the market for systems is large and diverse. I guess before I stop, I should make one note here about potential future work, which is you might notice a little bit of a tension here, which is I'm saying that as long as if we have more different models, then that's good. On the other hand, an implicit assumption we're making is that the downstream user is able to actually look at all the models and compare them and be able to rationally choose the one that's best for them. And as we have more and more models, that becomes harder. So this leads to an interesting platform market design problem of how can we collect information about different models so that the user can make good decisions and we can help surface these strategic tensions. Great, so that's my talk. Thank you all so much for your time, and I'm happy to take any more questions. Yes.
So going back to the first part of your talk.
Yeah.
So you had is equality or agreement sufficient and so on, but maybe is agreement necessary? So I mean, particularly if I'm the doctor, I don't care as much if I agree with the model as long as we satisfy the do no harm condition or the information aggregation condition.
Yeah.
And so could there be a more asymmetric version of conversation calibration which just satisfies that without agreement?
Yeah, good question. So we are certainly using agreement as a core tool to get our results, and we're definitely we have not proven that agreement is necessary. Certainly, interaction is necessary, but it could be possible that different models that if you don't care, I think the answer is that I would have to think about it more. It's a really interesting question, and we definitely have not proved that you need agreement. It just ends up being a very interesting intermediary object that helps us get a lot. Yeah.
Just to clarify, in the first part of the talk, you seem to be assuming perfect calibration, or does your result extend to approximate calibration, and how does the error come to the balance?
Oh yeah, so we're not assuming. I can see why you might have thought that because I did flash up a definition that said perfect calibration, but that was just because it looks simpler than the other definition. It does extend to approximate notions.
In the theorem, we had the 1 minus delta.
Right, so the 1 minus delta, right, so it's approximate in a couple ways. One way is this 1 minus delta and this epsilon, which are saying that you're almost agreeing, but you're with an epsilon. The other one is, well, what fraction of the rounds do we want that for? And then the third way it's approximate is that the way you're getting this is via some, if you really wanted to achieve this in general, you could do it via an algorithm that isn't perfectly conversation calibrated, but is approximately. And when you do that, you end up with this term right here, and this term goes to 0 as t gets large. And the exact rate it does that, if you apply standard worst case calibration algorithms, you end up with like t to the negative 1/3 there. Yeah.
So, quick question on the second part of your talk.
Yeah.
So you meant this market alignment.
Yeah.
So would an I think with an example, I think you went by with an example that would satisfy this. So like let's say in the Pfizer, JJ, whatever.
Yeah.
If each company said, what I want to do is maximize a weighted combination of the users, of the patient's benefit, and whether they use my drug. So it's you know. Alpha times this plus 1 minus alpha times that for different alphas.
Yeah.
That would satisfy this, right? In other words, if each one was a weighted combination of what the Alice wanted and their own thing, would that be an example? Because then you could.
If their own things were all zero sum with respect to each other, then it would definitely be true.
Like you're going to buy one medication. So if you're going to buy one medication, I want it to be my medication. Rod wants it to be his medication.
Right.
Each of us wants it to be whatever we're selling.
Absolutely.
And you're gonna buy one thing either way. So then you'd be able to average them up and
yeah, that's exactly
up,
right. Yeah, that's right. So the example that I gave, and more generally, like this idea of different competing medications, like that is something that falls squarely under market alignment.
Okay, good. Thanks.
Yeah.
So about the state of the nature bar, you are assuming everyone knows what is going on, right?
This is in the second part of the talk?
Yeah, in the second part. So I was thinking, do you know if your result extends to where, like, they know some different signal of the nature? Like, because if you ask the same question for, suppose they don't have incentives, they are all good companies.
Yeah.
So would they really, sometimes they give different answers because they just, their model is different, maybe they just come to a different conclusion. And I assume maybe you can model it with not knowing the exact why, but each one kind of have a different signal of the why or something.
Yeah, so they don't know the exact why. They don't know why at all. What they know is XB. It's just that they know how it's correlated with Y. So it's not that they know everything. It's that we're defining the set of information that they do have.
The Bayesian persuasion set. So why is the state of the world? So you don't know.
So they may actually tell, even if they have zero incentive and they all think about the utility of the Alice, they might suggest different actions.
Yes. Okay, if they have zero incentive. So in this simple in the example I presented here, where I'm assuming they all have the same secret information, they wouldn't.
Oh, yeah.
In general, in the work, they could have different information than they would. Another thing about this, which I think you're kind of getting at a little, is of course, in the real world, while I do think that this is like a good building block for what we want to understand, there's a lot of things that are different about the way that models are trained than what I'm presenting here. And actually, Haifeng, who just left the room, but I was going to shout him out and say that he has some really interesting work specifically on how you want to model Bayesian persuasion for AI models that gets at this idea that there's more than just the signal structure. There's also the framing that you have to do about the text being provided. And that might help explain the fact that even if you had models that were all completely just trying to help the user, you would still have variability in response.
All right, I think we're going to have to end it here. Thanks, Natalie.
Thank you so much.